Hello and welcome to another episode of All Things IDA. This is going to be the final video on the Appcall series. In today's episode, we're going to be talking about another aspect of Appcall, not related to calling functions, but how to actually leverage the Appcall intelligence to work with structured data. So we're going to be covering how we can parse data from the database given a known type information. So we point either to a piece of memory and we say this is the type. Please deserialize it from memory into a programmatic object, whether for IDC consumption or IDA Python. And we're gonna go the other way around. We're gonna construct an object in, let's say, Python, maybe through a dictionary with nested structures. And then we're gonna ask the appcall mechanism to store that object nicely while respecting that format into the native representation. So this is also useful for parsing data from memory while debugging and so on. We don't have to be debugging when we work with this, even though it's appcall, because we're gonna be, through appcall, we're gonna be using underlying regular SDK functionality, but they're nicely wrapped through appcall, especially from Python's point of view. So let's see how that works. Okay, so let's illustrate what I'm talking about with respect to having a structured way to access type information. So for example, let's jump to the image base here. And we know at the image base, we have a structure of the type image.header. If it's not here, let's bring it in. So let's make sure we introduce image.header. And now if we apply it manually, we have it. But this is not going to be necessarily pleasant if we are going to do it using basic primitives, meaning if we have that address and we want to extract ELFA new using primitives such as, say, get dword and so on and so on, we'd have to have the base of the structure, say get dword, add that structure plus 3c. So base plus 3c, get that dword. And so we will be littering our code with lots of hard-coded offsets. So there is a nicer way in IDA we can do that. And that facility is as well available through Appcall. It uses underlying SDK. So we can use that aspect of Appcall without having to be under a debugger. So let me take that header, make it a loader segment, and we can work with this offline. So we don't have to be debugging. And so here we are. I want to be able to programmatically grab the image.header header and access the fields without hard coding any offsets. So we're gonna create an empty snippet and we're gonna say image.header header type is using appcall dot, instead of typing proto like we had for regular appcalls, we're gonna use typed object. So this is another helper that will let us work with structured data retrieval or storage. So here we know the type. We're gonna say image.header header semicolon and like that. This will tell IDA, go parse that one and create that object that mimics the structure of this one. But this is only like a type. It doesn't know anything, doesn't have any value, but used as a template. So let's hard code an address. And now let's retrieve that DOS header. So we're gonna call a method that returns a tuple. Let's say DOS header. Now we're gonna use that object that is specialized to be of the form image.header, and I'm gonna ask it to retrieve at EA. If okay, print success, let's say, else print fail, for example. But I want to actually get those header and inspect it here. So let's run it. It worked. It managed to unpack those bytes into a nice object representation for Python. So here, if I say now those header dot, and now I can nicely access those attributes. So I can say dot e underscore lfa new. So here we should have image.header. So let's also import image nt header. So we imported the proper image nt headers, and as well, if I apply this by hand, I can see them in IDA, and it is clear that we have so many substructures. Dealing with this using basic primitives is not necessarily pleasant, but we don't have to create a structure instance to deal with this. So all we need really is just an address. So that's what we're gonna do. We're gonna continue that and also retrieve the image nt header. So let's create an image nt header type as well, same story. Let's wrap this in a function. and then we will fail instead of printing so much. Now we are also creating another one for image NT header. So where do we get the image NT header? So here we got the DOS header from the base. Now we can go advance with ELFA new field. So now we can say EA equal base plus the DOS header object that we deserialized to the field ELFA new, for example. And we can just for now print the image NT header, for example. NT header at, and we'll continue the script in a second. So here should be good to go. Let's also clear the screen and run it. Now we have the NT header, and let's just for illustration, let me apply it just to see what I want to pick up. So for example, we're gonna go maybe display number of sections. Let's try that. Okay, and let's retrieve first. So we got that here. And now we can say NT header equals as well inh dot retrieve at EA. Okay, and now we can say NT header dot file header, because so signature is at the top level. Then we have a nested structures, and I have another nested structure. Let's also capture the entry point, number of sections, and entry points. So here we can use NT header dot, and here as well we can say this one. This should be good enough. And maybe we can progress as well up to the sections and display the sections. Run. So entry point here we can see it's this. Maybe we can add to it the base. So let's add to it the base. Here we have it. Now we can, once we have a typed object, so I have this one. Let me execute it here and play with it outside a bit. Now that I have a typed object, that typed object, as we notice, we can use the retrieve method, but also before we talk about storing, it has a size. So we can directly ask for the size. So this is good. Based on our knowledge of PE headers, after the image NT header, directly we have the sections, image section headers. So let's open image section headers. And as well here, if we're gonna apply it manually, we have those stuff and so on. So with the number of sections, we can write a small loop for I in range this value. We're gonna do something with it. But before that, we can prepare the template. So what we want is just the image section header. And here, let's parse it. So image section header type equals as well appcall dot typed object of this one. And maybe we can also have the EA to point to just advance it since we are already at the PE header. So let's just advance it once by the NT header dot size. This will point us to where the sections start. So now we are at the sections, and now we can retrieve every section by itself. So okay, and section equal ish type dot retrieve at EA, and if not okay, let's say break. But otherwise, we can advance this time by ish type dot size. And as we do that, for every section, let's print just as much as we can, maybe the RVA, for example. Section I plus 1, RVA, or let's just compute the VA directly. Be base plus the actual value section dot, and let's see, here we have virtual address. Name, section dot name. Okay, let's see how that works. Yes, this is wrong, of course. We should be referring to the type. So it's actually, we're gonna advance here by type, not by the deserialized object. Okay, so really what we're doing is just a subsequent call of typed objects and advancing. So we can actually define all the type templates here. So what we need is DOS header, NT header, section header. We start by reading the DOS header, then we dereference one field, then we know where we are to get the NT header, we retrieve it. Now from the NT header, we access substructure, optional header, field address entry point, another substructure, file header, and now we advance past the NT header and start retrieving image section headers one by one, and advance to the next section by each section's size. Let's see how that works. And here we are. It works nicely. So we have the information we need, and the VA we can display it as hex, and we have nice information. So let's now look at the other way around. So I'm gonna do now the last demonstration with respect to storing the information. So let's clone this one, and I'm gonna keep it simple this time. So let's keep this like that. Okay, so a bunch of retrieval. So what I'm gonna do, maybe patch ELFA new, for example. So I'm gonna update ELFA new. Let's see how that works. So to keep it simple, I don't need anything. I'm gonna retrieve, this is good. Now let's maybe change ELFA new from F8 to AA, for example. So here now I say dos header dot ELFA new equals AA, and now just have to do the other way around. I did batch an object. Now I need to store that object. So for that, I'm gonna say, using that type template, instead of saying retrieve, I'm gonna say store. Now I don't remember the actual order. Let me double check. So let's see, dot store help. So it's first the object and the destination. Okay, so let's store now the updated dos header at the base. And this EA here, this is useless. This should be good to go. It returns true or false. So, okay, that's good enough. 0 for success and otherwise failure. Okay, so this should basically get it, patch it nicely without having to say put byte and hardcode offsets. And so we could have done it with nested structures and so on, and then store the base one, and it will store everything along with it. Okay, let's try run. And look at this here, we got now AA and so on. So that's it for this video. We explained in details and gave some ideas how to use typed objects and how to retrieve or store those information. I hope you found that useful, and I'll see you next time.